An Introduction to the Theory of Automorphic Functions by Lester Ford. Chapter 2, Groups of Linear Transformations. Section 11, Continuous and Discontinuous Groups. Let Z be an arbitrary point in the plane, and let us apply to this point all the transformations of some given group. Considering the positions of the points derived from Z by these transformations, two cases will arise. Either all the transformed points will lie outside a sufficiently small circle with Z as its center, excluding, of course, the identical transformation which leaves the position of Z unchanged, or there will be infinitely many transformed points clustering about Z. In the former case, the group is said to be discontinuous, in the latter, continuous. Thus, in the group of the simply periodic functions, example number 3 of section 9, given any finite point Z, there is no transformed point within a circle of radius omega drawn about Z. The group is then discontinuous. Similarly, the group of the double periodic functions, example number 4 of section 9, is discontinuous. In the group of real translations, example number 1 of section 9, on the other hand, we can, by taking k sufficiently small, obtain a transformed point as near as we like to the given point. This group is continuous, therefore. A group with only a finite number of transformations, as in examples 5 and 6 of the same section, is necessarily discontinuous. We lay down the following. Definition. If there exist transformations of the group, the identical transformation excluded, which change the position of an arbitrary point of the z-plane by an arbitrarily small amount, the group is continuous. Otherwise, it is discontinuous. If the formed point be represented by z plus delta z, the transformation can be written z plus delta z equal to the quantity az plus b divided by the quantity cz plus d, whence cz squared plus the quantity d minus a times z minus b plus the quantity cz plus d times delta z equals 0. If the group be continuous, there will exist transformations, whatever be the point z, such that delta z is arbitrarily small. Since there must exist transformations in which c, d minus a, and b are arbitrarily small quantities, but not all 0, for that is the identical transformation. In order that the group be continuous, it is not necessary that the coefficients of the transformation should vary continuously, as in the case in examples 1 and 2. Thus consider the group z prime equal to e to the in theta times z, where n is a positive or negative integer or 0, and where theta is incommensurable with pi. This is the group of rotations through positive and negative multiples of the angle theta. By rotating through the angle theta a sufficiently number of times, any point can be brought back as near as desired to its original position. Hence, the group is continuous. Continuous groups have been the subject of many investigations, particularly by Lie, and have yielded important results in the theory of differential equations. However, for a reason that will appear later, section 20 footnote, such groups play no part in the theory to which this tract is devoted, and we shall not have occasion to consider them further. An Introduction to the Theory of Automorphic Functions. This book was written by Lester R. Ford, M.A., Harvard, lecturer in mathematics in the University of Edinburgh. It was published in 1915 by G. Bell & Sons Limited, London, and is now in the public domain. It is read by Jim Renholt with programming and illustrations by Jim Renholt in 2019. Thank you for listening.